All right, last but not least, a little bit of stats. Still chi-square distribution, so we're not going to get super in-depth with any of this because a lot of it we covered in 10.1 already. We're just going to talk about a couple slight differences that are going to be in the test that you're going to be doing today. So in the problems that you're going to be doing today, we're going to have tables of values that represent our categories, and I'll flip back in a second. So something like this where we've got like types of business and then travel concerns, and we have in each of these little cells a specific row and column of information that we're looking at. Each of these represents an observed frequency, and we can also calculate expected frequencies for each of those particular cells in the table. So special names that they use for these, marginal frequencies, we're going to see are going to be the sum of the row or the column in a table. So we're going to have to add up the row, add up the column, and those numbers that we get on the side and on the bottom are the marginal frequencies. And then joint frequencies are the observed frequencies that are given to us already in the table. Assuming that we have two variables that are independent, and we're going to start using that word a lot in this lesson because we're testing for independence. We're testing to see if two variables are independent of one another. We can calculate expected frequency like you see at the bottom here. So we're going to sum up those rows and columns, and for each particular cell, we're going to sum up the row, multiply it by the sum of that column that the cell is in, and then divide by our total sample size. So we're going to practice that on the next slide. Okay, so first thing that we have to do, add up all the rows and columns. Sometimes that'll be done for you. Sometimes you have to do it yourself. This time we have to do it ourselves. All right, so I'm going to sum up my hotel rooms first. 36 and 38, 74. Leg room on a plane is a travel concern. 162, 28, and 36. And then sum up my rows, 36, 108, 14, and 22. Gives me 180 for that guy. 38, 54, 14, 14. Give me 120, bless you. And then if you want your sample size, n, you can either add up the total of the rows or the total of the columns. They should actually both equal the same thing, which in this case is 300. Okay. All right, so now to get an expected frequency, I'll use an E again, for a particular row and column. So let's say I wanted to know, okay, there were 36 observed people that traveled for business and were worried about their hotel room. We want to know out of 300 people, what would be the expected value for that travel, okay, concern. So how we're going to write that, that's in row 1 and column 1. So it's a 1, 1. That's how we write the notation. And then we're just going to multiply the sum on the top with the sum on the bottom and then divide by my sample size 30. So 180 times 74 are the totals for that row and column divided by 300. And I get 44.4. Okay, so now we pretty much need to do that 7 more times in this problem. So row 1, column 2, row 1, column 3, row 1, column 4. That would take us all the way across the top. And then on the bottom, row 2, column 1, row 2, column 2, row 2, column 3, and row 2, column 4. Remember, rows go across, columns up and down. Okay, so take a minute, finish out the rest of these expected frequencies. I'll give you a minute. Maybe we'll put them on the board even. All look good. What do you think if I add up all these numbers, I'm going to get 300? Okay, so just like our observed frequencies, our joint frequencies add up to 300, so will these. Okay, so now on to the hypothesis test we need to get to. That was just a little extra piece we need to worry about. So we're going to be doing a chi-square independent test. You can't see that, so hold on a second. There we go. Chi-square independent test is used to test the independence of two variables. So we're determining if, I don't know, travel reason and travel concerns are independent or dependent of one another. For example, if we were looking at that last group. Using this test, you can determine whether the occurrence of one variable affects the probability of the other. When we look up degrees of freedom on our chart in a second, we're going to be using that same chi-squared chart. Because we have two different categories, before we just had a K and we did K minus 1, and that's how we found the degrees of freedom. We're going to take our rows minus 1, so that's the categories across, and the columns minus 1, and then we're going to multiply those together, and that's going to be the degrees of freedom that we use. So for example, if I had a table with all of my frequencies that was 3 by 4, what would my degrees of freedom be? It would be 6. You just take one less than each of those. 2 times 3, multiply them together. Degrees of freedom we would use on the chart is 6. So that's how we're going to find that value. Level of significance is still going to be the same. When you do an independence test, the null and the alternative will always be the same. Okay, so the null is going to be that the variables are independent of one another, and the claim, well, the claim could be either, I guess. The alternative is going to be the variables are dependent of one another. Okay, so one depends on the other. All right, so let's try one. Here are the steps again if you need to refer back to them. Everything is the same as the previous lesson. Remember, it's always a right tail test, except for our claim's going to look a little bit different how we write the null and alternative and that degrees of freedom piece. Okay, we're going to do just one of these. So I'm going to do the one that has less numbers on it. So we're going to skip to the 2 at the bottom on the back of your paper there. We're going to do it together. All right, so it says the contingency table shows the results of a random sample of students by the location of school and the number of those students achieving basic skill levels in 3 subjects. At a level of significance of 0.01, test the hypothesis that the variables are independent. Okay, so I'm just going to go ahead and write my null and my alternative right now. So they're telling us to test that they are independent. So my claim is the null. So it is that location and subject are independent of one another when it comes to our test scores that we're looking at. And then they are dependent. One affects the other is our alternative hypothesis. Okay, so first thing that we're going to need to do is we're going to need to total up all these rows and columns because they didn't do that for us, and that's going to help us get those expected frequencies. So across the top, if I add all those up, I get 123. 63, 66, and 65 give me 194. Down the bottom, I'm going to get 106, 108, and it's like 103. And then add all of those up, so that's going to give me 317. Either way, I think. No, yeah. Okay, so that's going to be our N. All right, so now we want to find expected frequency. So what you can do on, and you guys have it on to the right on your paper there, is you can actually just go ahead and start filling this out. So remember, for the expected frequencies, we're going to do the row times the column and then divide by N, our total here, which is that 317 that we just found. The observed frequencies are the numbers that you have in the table already. Okay, and it doesn't matter what order you put them in when you fill these out. So I'll use the urban ones first. So 43, 42, and 38, and then 63, 66, and 65. And some people, when they make these, will also label them. They'll say like row 1, column 1, row 1, column 2, just so you can refer back to where these numbers came from. Okay, so then if I want to find the expected frequency that goes with 43, that's row 1 and column 1. So I need to multiply together the total from that row, that column, and divide by 317, which I'm going to flip back and forth here a little bit. So that's 123 times 106 divided by 317. And I didn't like that. There we go. I'm just going to round to 3 decimal places. So I got 41.129 for that one. Okay, and then we just need to do it 5 more times. All right, so 108 times 123 divided by 317. 41.905. Okay. 103 times 123 divided by 317. 39.965. Okay, now to my bottom one, 106 times 194 divided by 317, 64.871. 108 times 194 divided by 317, 66.095. And then the last one, 103 times 194 divided by 317, 63.035. And then I'm just going to double check that both of those, well, that one should for sure give me 317. That guy's good. Check the other one. Might be off by just a little bit because I rounded, but we'll see.
Hi, this is Miss McDonald. Hey. Oh. I had a feeling I would give it away. Okay. Oh, that makes me happy. Oh, good. Okay, well, thank you for letting me know. Bye. Okay.
Where was I? Anybody add that one up yet? That column? No. Oh yeah, 317. We're good. Right on the dot. All right. So you can skip these middle 2 columns if you want. I prefer to just skip them. And you can do this all in your calculator now if you want to, like we did before. So O minus E, square it, divide by E. You're doing that for each set. All right. And again, I'm just going to round to 3 decimal places. Subtract, square it, and divide. 0.085. Ooh, that one's tiny. I'm going to give this one 4 decimal places, 0.0002. All right. Point 0.097. Point 0.054. Another tiny one, 0.0001. Point 0.061. Add them up, and that's our chi-squared value. All right. Point 297 7.3. All right, find your chart. Here's mine, down here somewhere, maybe. All right, degrees of freedom, number of columns, and number of rows minus 1. We have a 2 by 3 table, so 1 by 2 degrees of freedom is 2. My critical value of chi-squared is coming from the chart. What was our level of significance? 0.01. So we're finding where those intersect. So let's see, 0.01, 2 degrees of freedom, 9.210. Okay, always a right tail test. So starting at 9.210, to the right is where the rejection region is located. Is our number in the rejection region? After all that calculating? No, it is not. So what do? Fail to reject. All right, and then what does this tell us? So we say there is not enough evidence to reject the claim that location and subject are independent. So this is telling us we can't reject it, so not 100%, but likely that it is true that they are independent of one another. One does not directly affect the other. We don't see that correlation. Okay? That's 10-2. That's everything you need to know to do your one problem. Any questions for me? It's the last lesson I'm going to teach you. That's it. What was that, Lauren? It's okay. You can come back and visit. Aww. Well, you have 25 minutes. Can you get one problem done and turn it in 25 minutes? And then you have no more stats? At all? Worry about it? Okay. What are we going to do on Monday? Study for calc. We got a whole 7 days in January to reset with these. We're going to be 9.5 hours away to that direction. Oh, wait, can you do that? It's not enough. But does it take 9.5 hours to get from one place in Ohio to another?
I don't understand.
No, it's just I'm going to come when she's going to.
Oh, like in college?
Yeah.
Like in the future?
Yeah.
I thought you meant like tomorrow.
No, like, oh, yeah, we're going to be 9 hours away tomorrow.
So you can meet in the middle,
Yeah,
right?
home's the middle.
What's in the middle of those?
Home.
Oh, okay.
We're in opposite directions.
Well, there might be something else that's kind of fun in the middle, no? Like if you did like a straight line, like a cool place to meet up and, no?